Hello everyone, welcome to the lecture number 44 of this NPTEL lecture series on charging infrastructure, and today we will discuss on the some of the aspect of transformer design, mostly the transformers which are used in isolated DC-DC converter. So if you recall, we have studied in detail about full bridge converter, its operation, and then we have seen different PWM methods which can be possible with the full bridge converter, and then we have seen the phase shift full bridge converter, its different modes, its different conditions for soft switching, and you can say the zero voltage turn on of the switches in both the leading and lagging leg, which we discussed in detail. After that, we moved our discussion towards a dual active bridge, where we discuss basic, or in briefly we have discussed the different operations of the dual active bridge. In both the converters, if you see, we use the high frequency transformer. Why we say high frequency transformer? Because that particular transformer sees the high frequency excitation or high frequency AC voltage is applied across the transformer winding. I mean, if you recall the, let's say, simple our dual active bridge. We quickly draw a dual active bridge. So from both sides we have, let's say, V in, V naught. On both sides we are actually applying the voltages, and generally the switching frequencies are kept quite high, going from 10 kilohertz to in upwards 100 kilohertz or 200 kilohertz, 300 kilohertz, and now people are also talking about in megahertz as well. So there, if you look very carefully in this thing, we are actually applying a high frequency AC onto the terminals of this transformer. So we can say that this particular transformer to be a high frequency transformer. So let us try to understand what goes in designing this transformer, what thing one need to understand, and what are the procedure, how to physically realize this particular transformer. Now if you look very carefully in our courses, in our undergrad courses of, we have already studied about transformer. So in transformer is basically consists of a core and a winding. Now core is basically made up of ferromagnetic materials, and the windings are actually wounded onto this in this manner, and finally it comes out like this. Here mostly in transformer we have two windings, one, let's say winding 1 with, let's say, N1 number of turns, and which is having the current going into the winding, which actually generates, if we take the flux direction, it is somewhere depending on that, and that flux is in the core, so we have defined that as phi c. Similarly on the other side we have another winding, where from the other side we have going like this, going like this, going like this, going like this, and then finally coming out from the behind. Here if we see this particular winding will actually be, if we say this is my I2 going into this one, this is V2 which we are applying, we are again having flux generated in this direction, and this flux gets linked with this winding, and accordingly the voltages are induced. If you connect the resistance or the load on this winding, then the current direction will be in reverse of that, such that whatever flux generated by this winding will actually cancel out by the flux generated by this winding, because here, because from the Lenz's law we know that the effect will actually oppose the cause. If this excitation current has some AC excitation, so this phi c will be having the varying flux, and that varying flux is actually cutting this winding, which actually induce the voltages at the terminal of the next winding, which has this N2 number of turns, and this flux is actually cutting down this area of the core, and let us define cross section area of the core to be AC. And if you look very carefully in this, if we see this particular flux is actually going into the core, and let's say this magnetic length corresponding to this flux line in the core to be my LC. Now if you see very carefully in this particular type of setup, we are actually applying this excitation current into one of the windings. Now we know that this core material is mostly are made up of ferromagnetic material, as a result of which what happens, where this ferromagnetic material consists of magnetic domains, and whenever there is no external magnetic field is applied, those domains are actually arranged in a random manner. So thus, as a result of which the net flux generated by those domains, because the domain itself produces the magnetic flux. So since they are arranged in a random manner, the net flux generated by those domains are generally equal to 0, and whenever this magnetic material which consists of a magnetic domains are placed in an external magnetic field, then this magnetic domain align themselves, I mean along the field, align with the field you can say, and as a result of which they generate a net flux, and that flux is actually lead to the magnetization of the core, and that particular process is called as the magnetization of the core. So that is why it lead to a curve called as a BH curve, where we have the external magnetic field applied onto the core material, and as a result of which there is a magnetization in the core, which actually lead to the generation of the some net amount of flux, and which is actually defined by this flux density term, which is called as a B. So this particular thing will have the shape something like this, where what happens the moment you are increasing the external magnetic field, the more and more magnetic domain align themselves, that is when net flux produced in the core gets increased, and there is a point when almost all the magnetic domains align themselves, and that is when the core gets saturated, or you can say that the flux in the core reach to its maximum value, and that is when you can say the core gets saturated. So that is why we see that after a certain point we see that there is no increase in the net magnetic flux density, even though my external magnetic field is increasing. And this, because of this thing, you know, this BH curve is one of the curve which actually determines how well the core material get magnetized, and how much amount of energy is needed to magnetize the core itself. However, if we see, while going in one direction it follows in one path. However, while going from another direction, going downwards, it actually follows the other path. That means this particular curve has some hysteresis. It is non-linear as it saturates beyond the certain value of H. So this is the BH curve, which is one of the critical core material properties. So whenever if we try to see this particular transformer, if we try to see our this particular transformer magnetic circuit model, from the magnetic circuit model we can then write, actually we can then draw the model, and we can then say our transformer will be something like, will look something like this, where we have N1 and N2 number of turns. We have, you know, we are actually applying V1 voltage in the transformer, and we have I1 current going into the transformer, and let us say, taking the generality, if the current from the other side also is going into the core, so we will get the core to be something like this, where the magnetic flux generates inside the core can be represented by the amount of current which is going into the magnetizing branch of this transformer, and this magnetizing branch of this transformer has the magnetizing inductance. Here we are not considered any winding resistances or the resistance corresponding to the core losses. Here we have assumed the transformer to be a lossless transformer. So we can then write the transformer model using the magnetic circuit model. So this is the transformer model what we have, and in this transformer model we have assumed that we have the magnetizing branch, where the amount of flux which gets generated inside the transformer is obtained by the current which is going through the magnetizing inductor. Let us define this as to be Im1, where Im1 is the magnetizing current referred to the primary side winding 1 you can say, and Lm1 is the magnetizing inductance referred to the winding 1. So then what we can do is, from this particular circuit model we can then define the magnetic field which we get generate inside the core to be nothing but, we can say this is N1 number of turns, and the current which is going through the magnetizing inductance, then divided by Lc, which is the magnetic length in the core. So, this we can say that it is nothing but the magnetic field which you get generate in the core, and which because of this magnetic field there will be the magnetization of the core, or you can say the alignment of the magnetic domain, which actually led to the net flux generated in the core. Now, this particular thing comes from the Ampere's law. We know our from Ampere's circuital law we can just circuital law we can obtain this particular thing. From this magnetic circuit model we can derive the current going through this magnetizing branch. Now, in this particular thing, if we see, because of this thing there is a magnetic flux, and that we can just say over here the amount of SC in the core will be lead to the magnetizing. From there we can easily draw the the marking in the BH curve. Now, in this, if you assume that there is some voltages which is been applied, so from the Faraday's law, from the Faraday's law of electromagnetic induction, we can just write voltage applied V1 to be equal to minus N d phi C by dt, which is, let us say here, N1 d phi by dt. Again, if we take only the magnitude terms, we can just write this V1 dt integration to be equal to N1 phi C, and that we can just write this particular term to be lambda 1, and this particular term lambda 1 is nothing but the flux linkage, and that is happening only when we are giving excitation only from one of the winding, that is N1 winding. Now, because of that, let us see what particular things we get. Now, if you look very carefully, this is the integration of excitation voltage V1 which is been applied in the one of the winding in the transformer. Since we got this particular thing, we can also write one thing, that since the current which is going into the magnetizing inductance is the one which is actually lead to the magnetization in the core, so we can then write our Im1 to be 1 by Lm1, which is the current which is going into the winding, and let us say V1 is the excitation voltage, this is V1, let us say it is some periodic voltage which has been applied, arbitrary periodic voltage. So, we can then write it is nothing but integration V1 dt. So, that this is the Im1 which is been going into the winding, and here if you look very carefully, this flux linkage is the one which will be defining amount of flux which will be generated in the core. So, let us say if we have our excitation to be, let us say if we assume our excitation to be sinusoidal, assume having some positive sinusoidal here and then some negative sinusoidal excitation which we are giving from, let us say V1 of t we are giving. If we take this V1 of t to be a sinusoidal excitation, so we will actually obtain, this corresponds to the maximum V1 which will be applied. So, that is when this is Im1 will be going through this one according to this integration of V1 of t, that is when my SC will be there which is coming over here, and that is why we have this point, my SC point is there, which is, we can say, nothing but corresponds to N1 integration V1 of t dt by LC, and this is multiplied divided by Lm1. So, at that point actually we are giving the excitation. Because of that, what happens is that the flux in the core will go up from this to this point. There was some residual flux which was there, which goes from this to this point, and then it forms actually, at this point it forms, let us say here it is del B which is there, which is coming over here, and then finally once it reaches in the negative direction, this negative direction will come over here, and that is when my BH curve comes over here, and then finally it forms B negative minus negative B, we have, and then finally this is my entire entire BH curve which gets enclosed while this particular kind of excitation is given to this particular core. So if you look very carefully, we have the AC component of this magnetic flux goes from del B to minus del B. Sorry, this is V2. So if we take our arbitrary excitation to be a sine wave T, and let's take the area under this curve in this particular part, let to be a lambda 1 by 2. We can then write V1 of t to be n d phi c by dt and 1 d phi c by dt. That we can write V1 of t and 1 phi c I can write AC into dBc by dt, because BC is nothing but magnetic flux density, and that BC is nothing but equal to phi c into AC. So that from here we can then put. So this one, if we take this one, we are having this integration times dt, we can say n1 AC, and this integration will, if we take only in half the cycle integration, flux density goes from 0 to del B. So we can then write n1 AC into delta B, and that integration we can get lambda 1 and divided by 2, so that we can get AC delta V into 2. This 2 term we get because we have only considered the half cycle, that means positive cycle. In other words, we can also say that the delta B goes from plus delta B to minus delta B, so we can write 2 times of delta B. Then with this phenomenon we will get delta B value to be lambda 1 by 2 and 1 AC, and that we can then write here to be nothing but equal to lambda 1, that we can write to be lambda 1 by 2 and 1 AC in this particular expression. So what we see in this particular thing, in the core, the whenever the excitation voltage is applied in this particular winding, there is a magnetic field which gets generated in the core, and that magnetic field is due to the current which is flowing through the magnetizing branch, the transformer, and because of this magnetic field will get magnetic domains in the core will get aligned, and as a result of which you will get some net magnetic flux density, and that we have understood how we can get for the simplest excitation, which is a sinusoidal excitation. Now this particular delta B, the magnetization which is happening in the core is actually responsible for the core loss, and because of the current which is flowing into the transformer, we have the winding loss as well. So these two are very significant, and both these losses are dependent on flux density, which we will discuss as we go along. And then our aim is to find out, we have to optimize this flux density such that we can able to reduce both this core loss and winding loss, because see in the transformer when we are giving excitation, we only have this winding which has resistance in the winding, so there will be copper loss in the winding, and then because of this magnetization of the core, that means the alignment of this magnetic domains, there will be some energy which is required to do the alignment, and that energy goes into the core, which gets converted into the heat and gets dissipated from the core. So that's why this core loss and the winding loss are very significant, and we need to optimize this flux density, which is delta B, to be such that we can able to reduce both these losses in the transformer, and along with that we should be in a position to actually obtain different parameters of the transformer, which includes several things which we need to calculate, like number of turns, the magnetic length of the core, the area of the core. Different design outcomes has to be obtained. So in the transformer design, if we talk about the design outcome, it is nothing but we require to define the core size, different dimensions of the core, like core cross section area, which is this AC which we are talking about. Then window area, this is the area, window area you can say in the transformer, which actually accommodate the windings, and this window area has to be sufficiently large enough where we can actually accommodate the windings. For example, if we look from this side, then our window area will be our window area will be this area over which the winding sits over the bobbin. Then we have the mean length per turn, which is nothing but, in the transformer, if we look in the transformer, we have several windings which is been done, and this winding goes from this particular surface to this particular surface facing that side. So we will have the windings which goes from here till here till here. We have the winding which goes like this, the winding goes like this, winding goes like this. So in the entire area, this entire area windings are wounded. So the mean length will be, the mean of this winding and this winding, the mean length of the wire which is required to do the 1 turn. We will see what is the meaning of mean length per turn as we go along. And then finally the magnetic path length, which is this particular length which we are talking about. So if we can able to identify these 4-5 terms, which is core cross section area, window area, mean length per turn, magnetic path length, we will be in a position to actually select our core accordingly, to select the appropriate core size, where we can ensure that magnetic flux density is below the saturation magnetic flux density, as well as it is the optimum value where our losses, the core loss and the winding loss will be the minimal. And then we have to also know what are the number of turns we have in different windings, because in transformer we have multiple windings. So what are the number of turns we have, then what is the size of the wire which is used to wound the transformer. So that is also needed, because wire size means generally the wire will be the copper wire which looks something like this, and this copper wire will be, if you look very carefully, the size depends upon the diameter of this wire. So that is the wire size we are talking about. And then we have the another important thing, like what is the peak flux density, because this peak flux density is essential to understand whether the core hits the saturation. Saturation means it's the value where at this place we have the saturation point. That means the point where all my magnetic domains get fully aligned and there is no further magnetization which takes place even if you increase the external magnetic field. So that is the saturation value. So we need to know the peak flux density which is there in the core. It has to be obviously less than B sat value. At the same time, it should be such that the losses in the transformer which we will discuss should be at its minimum value. This will be the design outcome we will obtain, when we design the transformer. Now these design outcomes can be obtained using quantities which are either specified, that means given in the specification, or needs to be obtained using the first principle. So for that, let us first understand the core loss in the transformer, and using that understanding we can able to estimate some of the design outcomes or some of the dimensional quantities. Now as we know that the core means the core material, the ferromagnetic material which is being used to actually generate the flux. Now in the core we have losses associated with that, and those losses are the hysteresis loss and the eddy current loss. There are two kinds of losses which are associated with that. The hysteresis loss is due to the energy required to change the magnetization of the core. What I mean by that, let us say if you have the magnetic core and you have applied a magnetic field in one direction, so the magnetic domain will align themselves with the field. Now when you change the field direction or external field direction, the magnetic domains rotates, and because of that rotation it requires some amount of energy to rotate those magnetic domains. So that energy will actually goes into the core from the external sources, and then it gets dissipated in the form of heat. So we can say that this particular thing is occur due to the rotation of the magnetic domains. So because magnetic domains resist to that rotation, and that is when it takes some amount of energy to rotate those magnetic domain. So because of that thing we have the losses corresponding to that energy, and that particular loss is called as the hysteresis loss. Now another kind of loss in the core is due to the current which gets induced in the core material. Generally the core materials are actually are conductive in nature. So the core material are conductive in nature. So because of that, whenever the core sees the varying magnetic flux, because of that varying magnetic flux there will be voltage induced in the core material, and because of the voltage induced there will be currents in the core material, and that currents is actually lead to the losses, it lead to the heating of the core, and that is actually called as the eddy current loss. So let us try to see how the hysteresis loss and eddy current loss will take place. First we will take our discussion on the hysteresis loss. As we mentioned, the hysteresis loss takes place whenever there is a change in the magnetization of the core. That means whenever the magnetic domain has to rotate, there is some amount of energy which goes into the core to rotate or to actually support that particular rotation of magnetic domains, and that is when it lead to some losses associated with that. So let us try to define, or let us try to derive quickly what will be the hysteresis loss, how the hysteresis loss will look like. So we can say that the energy which is going into the core and this energy is going into the core whenever there is a periodic excitation of the voltages which are happening from one of the winding, because we are actually exciting from one of the winding. So the energy going into the core obviously via winding, and in one cycle, obviously we have to write in one cycle. We can say, let us say we define this to be a W, which is, let us say we have applied the voltage V1, there will be current going through the winding corresponding to that, and that will be integrating over the time in one cycle. That could be one periodic cycle we can take, and this V1 excitation voltage could be any arbitrary voltage. Now this from Faraday's law we can write V1 to be d lambda 1 by dt, and that we can then write to be n area of cross section of the core, n1, let us say if there is been winding 1 it is been applied, n1 AC dB by dt. Obviously this dB is in the core, so we can write that. Similarly from Ampere's law we can write from Ampere's law my H into LC to be equal to N into I1 of t, which is going into the first winding, and that I1 of t to be HLC by N1. Now this I can put it in equation number 1, and that my energy lost in one cycle, or energy going into the winding in one cycle, because that energy is actually going into the core and it get lost. So we can then write down in this one. So we have N1 AC dV dt H LC N1 my dt. So this dt gets cancelled, N1 gets cancelled, and that we will have finally this AC LC comes out in one cycle, we have H dV. Now this is the energy lost in one cycle. So we can get the hysteresis power loss by multiplying the energy which is going into the core multiplied by number of times this cycle occurs, and this is nothing but given by, let us say P hysteresis is the our hysteresis power loss is nothing but whatever the energy which is going into the core, we will multiply it with the number of times this cycle occurs, and that that number of times we will just multiply it with the frequency, and then this is the energy, this is H delta B, this is for one cycle, this particular part. Now this is nothing but the, if you see this one, this is nothing but the volume of the core, this is the excitation frequency, if we see this integration h dB, it is for one cycle is nothing but the area of BH loop enclosed during one cycle of operation. So when the magnetic field is going in one direction, so our flux density is going in this direction, and it reaches to the point where it is given as delta B, where delta B is nothing but peak value of AC component of magnetic flux density on one direction, and then while going in a opposite direction we will get the delta B going in the negative direction, which is given as minus delta B. So this particular area is nothing but is the area which is enclosed in the BH curve during the one cycle of operation, and this particular thing we can say that this particular thing is nothing but is given in this particular part. So this, from this curve we can say that this is the area enclosed within the BH curve. So what we can say is that the hysteresis loss is directly proportional to the area which is being enclosed in the BH curve. Whenever this core in the transformer is being used in the circuit operation, what happens is that it is very difficult to evaluate this particular integration. So we can write our P hysteresis, or you can say the hysteresis power loss is nothing but we can say that it is proportional to F delta B raised to power alpha AC LC, where our alpha is the constant term and it is nothing but it is dependent on the material property, and also this F is the frequency of excitation of winding, and our AC and LC are nothing but the volume of the core, and we can say that this delta B is nothing but the peak value of AC flux density, and that is actually from the average value. So if we see, in this curve, it is the average value is nothing but 0.0, and when we say that delta B, it is nothing but the peak value of AC flux density going in one direction. So from the average value, this is our delta B on one side, on another side it is the minus delta B. Now this particular hysteresis loss we have written down for the case when our BH curve is not changing for the particular excitation frequency. So that means we assume that whenever we have given excitation of certain frequency, then the BH curve will still be the same. That means there is no change in the your mu value due to the other operating conditions. So this is what we get for the hysteresis loss. Now if you see, the hysteresis loss is proportional to delta B raised to power alpha, where alpha is nothing but the constant term which is dependent on the core material. Similarly, let us see our eddy current losses, how it looks like. Now in the eddy current losses, if we look very carefully in this particular thing, whenever we are applying current I in this particular winding, let us say N1, this one, there is flux which got generated in this one. As a result of this, if we see in this cross sectional area, the flux lines are coming and it is going into this cross sectional area. So we can just take this particular cross sectional area like this. If you look very carefully, the flux is going into this particular area like this, we can then draw in that way. Now if we look very carefully, because of this flux which is going into this particular cross sectional area, because of this thing there will be voltage induced, and because of that voltage induced there will be current which gets flows through into this particular area, and that current will be such that it will be opposing the cause due to which that particular current gets induced, and the cause is nothing but the varying flux which is going into the area. So that we will have the eddy currents which get induced. So this is nothing but the eddy currents which get induced due to this one in this direction, and the direction is such that the flux which is created by this eddy current is such that it is actually opposing that particular cause. I mean the flux which is actually causing that particular eddy current to be actually induced in the material. Now if you look very carefully, this particular eddy current is basically, you can say, it's a resistive loss. Why we can say it is resistive loss? Because if the core material, if the, you can say, if core material has resistive impedance, let us take that as R core, that resistive impedance term. So we can then write our P eddy current loss, or you can say our eddy current power loss, is nothing but proportional to the eddy current square times resistance of the core. Now this eddy current is actually, if you see, the amount of eddy current which get induced is directly proportional to the amount of voltages which get induced, and this voltages whatever will get induced is actually dependent upon the change in the, you know, amount of flux which is going through the I mean which is crossing this area of cross section, which is delta phi. And we can also say that our V induced, again the frequency with which that particular flux is changing, so we can then define is also proportional to the frequency of excitation, because depending upon the frequency of excitation, that means the frequency of the current I1, there will be the varying phi c which is having the same frequency as that of the frequency of excitation which is done given by the this current I1. So now we can say that from these two things we can say that our eddy currents which get induced is directly proportional to the change in the flux delta phi, and it is also proportional to the frequency of excitation. So from here we can write our eddy current loss is nothing but proportional to F square, if we put in this, times delta phi square times resistive impedance of the core, and it is considering we our core is having the resistive impedance, because if we have the capacitive impedance then this relationship may vary, it may also have some other frequency term coming into picture. So then we can write down that this PL, you know, if we put it this value in terms of AC flux density value, so it is nothing but delta V square, you know, A square AC square comes out, and this is R core. Now this R core we know that is actually, you know, proportional to the length of the core, or you can say the magnetic length in the core, and also it is inversely proportional to the area of cross section of the core. Now that implies my eddy current loss is actually proportional to F square delta V square, and this will go and this will become AC times LC. Now this AC times LC is nothing but, we can say, it is the volume of the core. So what we see is that in case of hysteresis power loss, our hysteresis power loss is proportional to delta V raised to power alpha, while our eddy current power loss is directly proportional to F square times delta V square, and there if you see the hysteresis power loss, it is proportional to the frequency and delta V raised to power alpha. Here our eddy current power loss is proportional to the F square and delta V square. Now if you look very carefully, this eddy current power loss and the hysteresis power loss are the losses which is happening in the core, and because of that losses the core gets heated up. Now if you see, it is very difficult to separately measure the eddy current power loss and the hysteresis power loss, because we only have the winding terminals, so we can only measure the amount of power which is going from the winding into the core, that means the amount of power loss which is happening in the core. So we can then from that we can only predict the overall core loss by measuring amount of power corresponding to the power loss which is going into the winding. And we know that our core loss is actually a combination of eddy current power loss and the hysteresis power loss. So that is the reason why the core losses are generally defined using the empirical Steinmann's formula, which is given as P core, which is the core loss. Core loss, overall core loss is nothing but equal to K core delta B raised to power beta AC LC, and this is for a given excitation frequency, and purposefully this particular excitation is nothing but the sinusoidal excitation, and this particular formula is the empirical formula which is also called as the empirical Steinmann's formula. Here if you see, our K core is the constant of proportionality and it depends on excitation frequency. That means for different excitation frequency this K core value will be different, and it also has this beta term which is the exponent term, and which is obtained from manufacturer's data sheet. So this is actually determined by the material property. So for different material it will be this beta value will be different, which you can obtain from the manufacturer data sheet. Generally the beta for ferrite material is nothing but in between 2.5 to 2.7 for ferrite materials. For different material it will be different. So if the ferrite is made up of different alloys of different material, then depending upon the concentration of alloys this beta value varies between 2.5 to 2.7. So the manufacturer generally provides this P core value, and this P core we can write this P core, this if we, this is nothing but our, if you see this one, this is nothing but our volume of the core. So we can then write P core versus volume, or you can say core loss per unit volume is nothing but equal to K core delta B raised to power beta. Again this is for a particular excitation frequency, and that excitation is nothing but the sinusoidal excitation. So generally the manufacturer provides this core loss per unit volume curve with respect to the various value of this delta B, where delta B is nothing but we can say the peak value of AC flux density. Generally the manufacturer provide core loss per unit volume versus delta B curve, and if you see those curve it looks like, for different frequencies they will provide the curve, and this is nothing but F1, F2, F3 so on. Assume this is F6, or let me one more thing, F6. So here for F1 is greater than F2 is greater than F3 so on greater than F6. That means for the same delta B the core loss per unit volume will be more for higher value of frequency of excitation. So that is what we will get the core loss per unit volume. Now this is nothing but the logarithmic curve. The logarithmic curve, it is generally it is the logarithmic curve which is been given in the core data sheet. That means core material data sheet, they will generally provide this core loss per unit volume versus delta B curve. Now depending upon the chosen core the volume can be obtained, and from there we can roughly predict the core loss which is happening in the required core material. So in this thing what we have understood is that my P core is directly proportional to delta B raised to power beta, where beta is nothing but somewhere value between 2.5 to 2.7. Now we know that our core loss is a combination of eddy current power loss and the hysteresis power loss. The eddy current power loss is proportional to delta B square, the hysteresis power loss is proportional to delta B raised to power alpha, and so that is what it becomes very difficult for one to actually predict what is the core loss, because we cannot directly measure the eddy current power loss and the hysteresis power loss. So that is why generally they provide this core loss using the empirical Steinmann's formula, which is shown over here, and this is especially for one particular excitation frequency, and that excitation is nothing but the sinusoidal excitation. For excitation other than sinusoidal, you may have to use the modified Steinmann formula and then able to predict what is the core loss which is happening in the core of the transformer. Now if you look here, generally this K core, which is the proportionality value which depends upon the excitation frequency, this K core one can obtain by taking the curve for core loss per unit volume versus delta B for one particular frequency. We can take 2 points, two different points, and then from 2 different points we can put it in this formula, and from there we can predict what is my K core value, because for 2 different delta B's you can, from there we have 2 variables K core and beta sometimes you can also know. So from there we can calculate the K core for different excitation frequency if we have this particular curve. Now we have already know that from Faraday's law of electromagnetic induction, from Faraday's law of electromagnetism, we know that our flux linkage is nothing but equal to integration V1 of t dt, where V1 of t is nothing but the arbitrary, we can say arbitrary periodic input given to the primary winding, and we have calculated this thing, and we got that the, in our previous discussion, if you see, we got that the peak value of AC flux density is nothing but, what we get is delta B is nothing but lambda 1 by 2 N1 AC, where this is nothing but the area of cross section of core and N1 is nothing but number of turns in the primary winding, or you can say winding number 1 or winding 1, and this is nothing but our flux linkage which is happening in winding 1. So in this particular lecture we have understood two important things, which is the core loss, and we know that our core loss is proportional to the delta B raised to power beta, and along with that we have understood that the peak value of AC flux density, or you can say the maximum flux density which is there, is nothing but can be calculated by doing the lambda 1 by 2 N1 AC. Now this lambda 1 can be obtained by integrating the V1 t dt, that means the arbitrary periodic input which is given to the primary winding, because depending upon the operation of the circuit you can get the different kinds of periodic excitation or input which is being given to the primary winding. So from these two things we have understood how we can obtain the delta B, and obviously we always wanted that this maximum value of AC flux density should be less than the B set. It should not go beyond the saturation value of the magnetic flux density. So here if you see, this particular point is nothing but B max. So we must ensure that the delta B must be less than the saturation value of magnetic flux density, and at the same time it should be such that we can get the required flux linkages such that we will get our proper magnetization of the core. Thank you very much for patiently listening to this lecture. Thank you.